You should also share your screen.
I am sharing. Yeah.
Oh, you're sharing my desktop.
Yes.
Yeah, and it's up to you if you want to show that loading time or not. It's really up to you. I tend to get it because I don't want to launch the content. Some people don't. Yeah.
All right, this is my last boomer question. Oh,
Okay, I guess we can get started. Oh yeah, you would also want to use the mic to make sure it's on.
hold on, let me click on first.
Hey, welcome back to CS 198, 126, lecture 10 on sequence modeling. Some announcements to get started. Quiz 4 is due tonight. It's on object detection and segmentation, the two topics that we covered last week. Quiz 5 has been released today. It's going to be on today's topic, sequence modeling, and Wednesday's topics, which is on transformers. Finally, homework 2 has been released. Since there was a delay in getting homework 2 out, we have adjusted the due date from this Friday to next Wednesday. I'll get the autograder up as soon as possible. This homework is on implementing and training a ResNet, and this is going to be slightly longer than homework 1. So we do recommend that you get started early because you're going to be training these on Google Colab, which do have GPU limits, and we want to make sure that you can still squeeze enough GPU compute out of Colab before the due date. Yeah, I don't have any more announcements. You can get started.
Awesome. That's perfect. Today's lecture is going to be on sequence modeling. But before we get into sequence modeling and why that applies to computer vision, it's important for us to ask ourselves a more important question. Let's go to military law and actually start there. The Uniform Code of Military Justice dictates that any officer who sends a soldier out to battle without a weapon shall be court-martialed. And so why does that apply to us today? Over the past 5 years, we have seen one of the greatest revelations in computer vision, and it does not come from our own visual processing within V1 within the brain or V2 or any of the other neural systems. It in fact comes from sequence modeling. What has language taught us about vision the way that we see? More so, what has language taught us about how we can improve upon the way we see? And so today, I'm going to be presenting to you one of the most foundational visions for how we are changing computer vision today. And that has to do with the way that sequence modeling now begins to tie into computer vision. In particular, we'll be going over sequence modeling techniques, their limitations, and ultimately ending on why sequence modeling ends up being a very nice framework to think about vision today. So let's look at the above. All of the following are examples of sequence modeling tasks. We have both audio on the above, as you can see the time series down below, and on the y-axis is frequency. We also have weather, which changes over the course of time. And we also have images, in fact, as you can see in the pixel grid. There are models like ImageGPT, which go about shooting computer vision exactly like language models do. Can you train a GPT-based model to predict the next pixel in an image? It turns out, in fact, you can. But the one that most people care about, and the one that's become most predominant, is language. So today we're going to understand why language and the paradigm that we've created to solve language modeling tasks actually goes and applies here into computer vision. Now, going more deeper into natural language, these are the great feats that we've been able to accomplish using sequence modeling. We have machine translation, we have chatbots, sentiment analysis, part-of-speech tagging, question answering, text summarization. Everyone here is well aware of ChatGPT and GPT-4. But why do we care about that with relation to vision? We care about that because of the way it's been able to utilize compute in a never-before-seen way. This is why the paper Transformers has become so predominant in the field. And that's because it allows us to think about sequences and time series in a way that no other framework before us has. And in particular, it's allowed for very, very beautiful scaling laws. So let's talk about what we're actually going to talk about today. We're going to start with sequence data. We're going to talk about the goals of sequence modeling. Then we'll go into the classical methods of recurrent neural network and LSTMs, embeddings, and then positional encodings. And all of this should lay the groundwork for the reason that we actually treat images sometimes as sequences to go into both the transformer and the vision transformer, which has now become the predominant framework for very, very high performing computer vision models. And we'll talk about why some of these models have been able to succeed. But before we can talk about today's current success, we have to go and talk about our previous failures. So today we're going to see why we failed in the past, what we can learn from it, and then how the lessons we've learned along the way in language actually make a lot of difference today in vision. Let's talk about sequence data. As we might all be thinking right now, this guy's standing up here for some reason talking about sequences when we stare at an image and we perceive it basically in an instant. We'll get there. Basically, in a week from now today, you'll be learning about vision transformers. And the paradigm of vision transformers is that there is a paper released out of Google, and it's called a 16 by 16 pixels is a word model. Sorry, I'm forgetting the name of the paper. But what they propose is that if you block up an image into just 16 by 16 pixels, treat that as a word, you can feed it into a transformer architecture and perform better than any of the current vision models that were trained at the time. Not only can you train better than them, but you have superior scaling laws and superior compute utilization. They fundamentally reframed how we think about vision. No longer is it convolutions or seeing an image more akin to the way like the human brain does. They went and totally changed the paradigm to thinking about it as a sequence modeling task. Let's talk about time series data and keep going back to why time series is a very, very important task and the lessons that we can learn from time series. So as we are all kind of familiar, time series data is just data recorded in a series of temporal steps. So weather data, how does weather at the beginning of the day change over the course of the day? This is a very important problem. We have people here at Berkeley in the ML for Applied Sciences lab studying stochastic differential equations in relation to weather prediction. This is research that's going on right now here at Berkeley and actually achieving very, very good results. And that's one thing that people come back to. But the task that people typically care a lot more about is language. Language evolves over the course of time. And so you can think about it in an autoregressive series where you predict one word, then you predict the next, the one after, and the one following. And that's been the paradigm that's allowed language models to succeed. Other examples can be music and audio. How does frequencies in the spectrogram change over time? As well as how can we think about this maybe in terms of videos? Videos can be seen as an agglomeration of frames that are presented one after another after another. And so even without me making the big claim that images are akin to a series of words, we can even just think about videos and the fact that videos themselves are represented in a time sequence. So this all kind of builds the picture that time sequence data is not only an important task, but can in fact be now related back to computer vision. We'll start with videos at first, thinking that maybe videos are a bit more natural to think of as a time series. But then when we come and talk about vision transformers in a week from now, we'll see that they're actually one and the same. This whole time, we've been thinking about pictures as a one and done kind of thing, but you can use the same techniques from sequence modeling to actually go about and derive the same exact techniques we've talked about before that convolutions have succeeded in, but so can sequence models. So the major issue that actually comes with using time series data is that we have many, many, many samples that we're looking at once. And we want to take from all this information one sort of message or one takeaway. Looking at the above at like this audio data, that's a lot of information to process. Certainly I can't do it justice by looking at it as a picture. And there's many different things you have to represent. Like think about the rate that we're actually encoding some of this information. Like a few kilobytes sounds small on a computer. When you think about that in terms of processing that, at least like first principles, like how could you as a human stare at the like spectrogram data and interpret it over time? It's really challenging. And the problem doesn't get easier even when we have a computer to try and do this computation for us. We're still stuck in the loop of us having these singular time steps full of data, let alone chained in a series. How do we not only represent each step of time, but make a story that's complete out of every single step in time? This is the great question that sequence modeling poses. How do we go forward from just a singular instant in time to multiple instances of time and reveal the great story that lies within? Let's start with text, probably the most natural and the one that we'll keep looking to because that's honestly where sequence modeling is best. It's just the most prolific form. What we actually do in sequence modeling for text is treat each word as a token. This is actually a little bit more convoluted if you read like recent token literature, but for ease of argument, today we're more so just going to call it every token is a word. What that actually looks like in practice is every token is maybe a fragment of a word or maybe a couple words joined together. There's a little bit of like information compression theory that goes into how you design them. But you're not losing much generality when you just think of every token as a word. So now that we've at least decided that every word is a token, how do we go about representing our data as it? Right here, we can create a vector that actually one-hot encodes every single sequence into a vector. So take Rome, Paris, Italy, and France. This is really hard for us to manage as strings alone, but as soon as we can transform it into one-hot vectors, where we've told the computer exactly which elements of a vector each word should be represented as, you can go and just translate Rome into the first column, Paris into the second column, Italy into the third, France into the fourth, so on and so forth. And so you've composed a large enough vocabulary to actually answer your question. But as you might be seeing or might be thinking, these vectors are huge. I think GPT-4 is like 65K tokens in terms of its vocabulary, or at least the other models are somewhere within that range. How do you actually go about dealing with all that at once and operating on one-hot vectors? It's not very natural. And we'll get to how we can kind of handle this later when we go and talk about word embeddings and the way that we actually go about transforming one-hot vectors into more of a continuous space. But for now, keep letting this idea marinate, that at least within text, we can kind of transform every single singular word into a vector representation. And that's the major takeaway from one-hot encoding, and particularly this example. Now let's go on to the generic goals of sequencing model. We'll tie back in why text matters a lot for this, and kind of some of the things that our representation with this one-hot model has kind of allowed us to model with. So one thing that we'd like to do is handle arbitrary length data. Many different things do not come on the same exact timescale. Language, for example, is maybe the greatest example. Not every sentence has the same number of words. So how can we create a generalizable model that can handle different inputs? What we've been thinking about a lot right now with like convolutions or normal image models, you all assume like a fixed size. Like at the beginning, you write your little data pipeline, you're resizing an image 224 by 224 or 3 color channels. We go into the real world and that's not necessarily a true assumption. And we definitely can't make that assumption when we're looking at textual data and trying to model according to that. So we have to start incorporating this into our new solution for how we can treat sequences. We need to make sure our models can work on an arbitrary length of data, not just a fixed length. And then we have the actual sequence modeling paradigms. One very common thing that you think about is like sentiment classification. This is something I was doing at like my past internship, is actually just taking in like movie reviews, for example, and determining whether or not the reviewer was positive or negative on it. And there's also machine translation. This is where the foundational transformer paper actually comes into play. The great thing that they did in that paper is propose a new way to do like just pure translation tasks. English to French was the one that they bring up in the paper, and they create like an encoder decoder architecture that this sequence modeling paradigm is where it truly comes to fruition. What they proposed in that paper was a way that was able to utilize more compute power than has ever been seen before, and is able to pre-train in a much more parallelizable way some of the methods we talked about today. And one of the final things is image captioning, which maybe combines something we're a little bit more familiar about now, which is representing images, but then also going about and giving an arbitrary length output. Let's say, for example, we have like literally just a picture of like this slideshow. How can you go and take a model, we could look at this picture and then output a textual description of what's going on? At least right now with the toolkit we've developed, that seems really, really challenging. Like how many words do I want at the output? What exactly do I want to even describe in this image? How can you represent them jointly and make the two models talk to each other? Because even if we had like a vision model off the shelf, or we had like a language model off the shelf, getting those two to fuse together and actually talk is quite challenging. So in order to even approach any of these tasks, we have to be able to think about the way that we can support variable length output, given the tasks above. So now we get to like the major thing that we kind of think about within sequence modeling. And that is like just representing it as like what goes to what. Computer vision, at least everything we've talked about right now, falls into this one-to-one paradigm. We have one image, we have one output, it's happy. There's like these beautiful models, you can code them up super quickly, and life is good. Life has been great. I mean, think about it. It's like magic when you like watch AutoGrad work, your loss goes down, accuracy goes up, but not every problem is so easy. What happens if we're doing image captioning? That fits the paradigm of one to many. We have one image, but many words that we want to output. Or how about just sentiment analysis where it's flipped on the other side? We have many different words that we're trying to look at once, but only one output we're trying to curate. Then we get a little bit more challenging. That's just machine translation. How do you take a whole English sentence and turn that into French? There's not even a one-to-one lookup table that you can construct where maybe we can be like, oh, dictionaries are perfect. Oh, one lookup time, we can look at every single English word, map it to a French word. Thank you, we're done. But such is not the case. Such is never the case. And that's research as a whole, but because it's never the case, we get beautiful solutions. And that's what I'm here to harp on today. There's beautiful solutions within sequence modeling, and we are going to elucidate them. Then last but not least, we have video classification, or at least by frame, where you take every single frame of a video and try to classify whether or not some action is occurring. One example I know of that's deployed into the real world is bedside classification. If you have a patient that's sitting in a hospital bed, how do you know if they're actually in the bed? Not as simple as you'd like to believe. It's actually like a real R&D challenge, but you have to go about every single frame of the video and determine if they're in the bed or out of the bed. And that matters because maybe the patient's having like an adverse reaction to a drug, or maybe there's something else life-threatening going on with the patient and you need intervention. So these systems make a lot of difference in the real world if we're applying them. And there's many different ways that we have to construct our mappings. Here are the 5 major ones: one-to-one, one-to-many, many-to-one, many-to-many, and many-to-many again, but in a different kind of paradigm. Then one of the other things we have to take into account is long-distance relationships. Convolutions in particular get at this, but they get at this in a struggling way, where when you stack many convolutional layers, only at the end and only in the final layer can two, like, let's say you have the right hand of the image and you have the left hand of the image, those two sources of information and data only commingle in the much further layers once you have enough of the spatial recognition. But at least within the first layer, like your first 3x3 convolutional grid, those two regions are never taught. But in language, we can't always afford ourselves that, or many other problems, we can't afford ourselves to be looking at two far apart pieces of data and not letting them commingle for long enough. So how can we go about thinking about interpreting a sequence and letting the two pieces of information that are far apart, but actually necessarily dictating one another, talk? One example I can think of off the top of my head is in German. There are these certain verbs that actually, when used, kick a second verb to the end of the sentence. So like, ich kann Fußball spielen means I can play soccer, but ich kann means I can, but spielen, the actual word in the sentence, gets kicked all the way at the end. How can you model a dependency where these words aren't together? And that's what long distance relationships will eventually try to make sense of. So now you've heard me ramble for a very long time about sequence modeling. Why does sequence modeling matter? Let's at least talk about one way that we try to go about this, and then also go and tear it down. And if anyone has questions at any point, please feel free to stop me. I tend to ramble for a long period of time. So everything that we've looked at so far is one-to-one. We have an input layer, we have a hidden layer, we have the output layer, but we've subsumed that the input is always the same every single time. And so how can we kind of stretch this definition, maybe even use this exact model and treat variable length sequences? Thus, we come to the recurrent neural network. What it proposes is to create kind of a shared cell that processes every single element of the sequence. What this looks like in practice is at every single time step, you'll receive your temporal input, but then you have this cell, which kind of has like a memory to it, or a so-called hidden state. And what we can let this hidden state do is go and feed into the next example. So at x0, you either have like a randomized vector or some known vector that you're fed in ahead of time. But where things get interesting is that x1. x1 not only receives the input x1, maybe we're classifying the sentence representation of like a movie review, and we're trying to determine if it's positive or negative. And the reviewer states in that sentence, the is the first token, and reviewer is the second one. Now has more information than just reviewer alone. We have to think about how we can pass the information from the. And so what the RNN proposes is to have this hidden state and pass it forward to the next one. The, if we assume that was x0, will now get transformed and passed in through its hidden representation to x1, which was reviewer in that example sentence I gave. And so what we're doing here, we'll represent it mathematically in a moment, so I'm not just drawing pretty pictures and saying we've solved language modeling, is that we've now given a way to actually, one, share parameters. This hidden state is the same across everyone, or this hidden weight matrix is the same across every RNN cell, but we've now given it an idea of like temporal state. Because when we feed in our hidden representation or our hidden embedding from one cell to another cell, we're giving it a memory of sorts where it can memorize or at least make some sort of signal representation of the previous things it's ingested. So if you take away anything from this weird picture, It's this arrow going to the right. This arrow going to the right is the first breakthrough that leads us to at least generalizable sequence modeling using neural networks. So this idea of the hidden state is one of the most important things. This is what lets us actually see time. By having a hidden state, we can keep track of everything that we've seen in the past, but now give it to what we're seeing in the future. So let's think back to what I was saying about how we have those one-hot encodings. Why is a one-hot encoding important? Without even talking about weight embeddings or more like complicated things, let's just say that we had our current neural network of one layer in the middle where you feed it, the weight gets transformed, and then the hidden state gets transformed. There's two learnable parameters in an RNN. Weight matrix for input, weight matrix for hidden state. What we are now allowing ourselves to do by having this hidden state is we're able to use our very comfortable neural network paradigm, input-output. Input goes to input matrix, and then finally to an output matrix that determines what is outputted. As well as one more special component, which is the hidden state matrix, the hidden state parameterization, which from the previous time step will be passed to the next time step or the current time step, and it's then multiplied by the hidden state matrix. And that lets these sentence components communicate forward in time. So you're not just feeding in one example at a time, but you're feeding in one example and it's past information. So again, this is the same thing that we talk about with normal feed-forward neural networks, but for the first time in history, we're actually giving it information that propagates forward in time instead of just treating it as this singular block in time where nothing communicates. We've now developed some sort of measure of time. So let's actually go through an example. We have the quick brown blah, blah, blah dog. It's a fun example of showing up fonts. The quick brown fox jumps over the lazy dog. What we're actually inputting at the beginning is the quick brown and dog. And in this case, we're going to try to predict the next token. And the next token at every time step should be represented as the output. So output zero in this case should be x1, x2 for O1, so on and so forth. And the great thing that we can also do is that we can go and stack these representations. So the thing that we enjoyed much about neural networks to begin with is that we can create more and more complicated functions by introducing nonlinearities in between these layers. And we can do the exact same thing with deep RNNs because all that we've fundamentally done is give like an extra parameter matrix to our current neural network. So all these like fun little tricks that you can do about like having deep networks still work here. And you still just go about propagating forward in time. But you've now given yourself the ability to model time. And that's the only thing I'm going to harp on. RNNs suck. They've kind of been deprecated. No one really uses them in research. Sometimes they do, but there's always a reason that something else didn't work. But the one thing you have to take away is RNNs were the first time that we were able to give neural networks an understanding of time. We let neural networks talk to the future where no other model could. So let's actually go about a character level language model. Before we were trying to do words, now let's make it even simpler. Let's say we only have 26 things that we're trying to output, and we literally just want to predict the character that comes next. This is actually like a fairly challenging task. I tried running one of these myself. They don't converge very well. That's just because RNNs in general are a bit finicky. But this is a very simple way that you can at least show about using the utility of an RNN, and that is just predicting the next character. This is akin to how like ChatGPT, GPT-4, or like GPT-Ns work, is you just predict the next token, but here we've relaxed it a little bit and said, let's predict the next character. Let's see what the next character's got in store for us. And so each hidden state, M gets passed as an input. It does this linear algebra, does all the fun stuff, gets passed through an O, and its goal should be to predict that A comes next. Then A gets passed in, it receives the update information from the first time step, which is when the M got passed in, does more linear algebra, outputs the O, fingers crossed it was a C, and so on and so forth. C receives the hidden temporal state from M, A, and C, and then it tries to do an output. Everything went well, output is H, so on and so forth. And so now this is one of the first times we can actually see some sort of temporal representation in our data. Let's talk about if we did not have these hidden layer connections of this forward arrow, which is essentially this whole lecture today, that like a forward arrow in time is this big revelation. All we could ever do is take M alone and output A. That alone is like fairly linkable. Like every time you see an M, output an A. But how do you know when you've received an A to map to a C? That's the thing that RNNs actually let us tackle. It gives you a history of what it's seen before, and it can try to agglomerate those statistics into some sort of actionable insight for predicting what should come next in the sequence. So let's talk about an implementation, because I can show you a lot of pictures. I can tell you this is how things work, but until we dive into some of the math, I'm just talking at you. And so this should look quite familiar. We can relax the equation h of t into something that you've seen more commonly in neural networks by just getting rid of this WHH times h of t minus 1. And we've just rederived the neural network. So the big difference here is that we do have this term included. We have a nonlinearity, we have a weight matrix, and we have our current input vector. And then you also have YT, which is linear transformation. Don't have to think too much about that. But this tan H could be a choice. It could be a sigmoid, it could be a ReLU, it could be something more complicated. GayLU, whatever you think is most interesting. But the big thing, the only thing mathematically we're doing is just adding one term. We've been able to give our models a sense of history, a sense of time, which is one term in an equation. It's very naive and very simple, but it's very beautiful because no other model could have done this. So all we do is we say that your hidden state is some nonlinear activation of your previous hidden state, h sub t minus 1, times your weight matrix, and then a second weight matrix for your input multiplied by your input vector. So weight matrix times your input added to your weight matrix times your previous hidden step. And so if you take away anything from this equation, there's a lot of letters, a lot of junk. Take away this one fact, and that is for the first time, we've been able to pass a previous state from a neural network to our current state of a neural network and do mathematical operations on both of those at the same time, which matters a lot because this is the only way that we can actually go about taking in sequences and thinking about them in a one after another fashion. So did we get to where we wanted? We kind of did, kind of didn't. Research goes on, but why did we get something good? And then let's maybe talk about why we didn't get somewhere great just yet. Can we do arbitrary length data? Yes, we can. We can input something at time x0, get the time x sub t. We've done what we wanted. I've never told you where we have to stop. We can stop whenever we'd like. We can go for millions and millions of characters. It's actually better than transformers can do today. So that sounds decent. Are we still modeling sequences? We are. Time goes to time step after another time step, and life goes on. Long distance relationships. We say yes in theory. How much can you really encode into a singular vector? Let's say our hidden state is 512 dimensions, and you're on to your millionth word in a book or something. Do you think you could actually remember that in 512 dimensions? Maybe if you have some insane precision, something beyond what computers are doing today, sure, maybe you could. But we haven't really cracked. We feel like we have. We got a vector. We're doing math. Come on, we have a pretty equation. We've kind of done what we were looking for, but we haven't actually numerically gotten the results if you go and look at any of these papers just yet. We've solved our task on paper, but we haven't solved it evaluation-wise. And if there's any lesson this field has taught us, the only thing we care about is when you can make a bold number in a paper and say it's bigger than your previous competitor. And we haven't quite gotten there yet. We've at least gotten there so far, but have we gotten to a bold enough number that you can put in the real world? Or are you kind of just bragging to your colleagues about my number is bolder than yours? That's at least where RNNs get us. So one other fun thing, at least one other side addendum to make, is that with recurrent computation, the number of model parameters does not actually increase as time steps increases. One way that we could have thought about this problem at the beginning is fixing our sentences to be only 1,000 in length. Then for every single input step up to 1,000, we have a literal weight that goes to it, and you try to predict its output. But there we're fixing the parameters ahead of time. And let's say instead of 1,000 words or 1,000 characters, we wanted 2,000. We don't have to train a whole new model, and we're training with more parameters, but we don't have that here. In the recurrent version, the recurrent neural network paradigm, we don't actually have to increase parameters, which is pretty nice. But why? The why happens because we shared parameters to that hidden state. The W sub HH is the big breakthrough. We don't have to forcefully jam more parameters because we're damn, forgot that we might have a user that wants 1,002 tokens instead of just 1,000. We can actually just go about and compute that. So what happens if we're not just going forward and backwards? There is a model called the bidirectional RNN, which actually kind of dictates that you can sequence all at once. So this doesn't work anymore. Actually, you still can fit it if you have a task where you're trying to predict the next token, but it's a little bit more messy. And the great takeaway is that, you run it forward and you run it backwards. And maybe something that got lost when your time step x0 was trying to get the time step x of t, or some temporal piece of information you're trying to convey. and it just couldn't squeeze through like 512 dimensions in your vector space or something like that. Bidirectional RNN is like, yo, what if we just kind of ran it both ways? And it works a little bit better. And it essentially just says, what if instead of only running time x0 forward to time x t, we also started at x sub t, ran backwards, and went all the way to time x sub 0. And then you kind of just concatenate or add the two together, perform your same linear algebra, get a little bit bumped up in score. And it works, but it doesn't work great just yet. And we'll start getting to some of these issues. So I say there's all these impending issues, but I haven't really talked about why they exist. But before we get into that, we'll talk about one more way that the RNN can succeed, but still keep in the back of your mind why the RNN isn't where we stopped. Maybe like even right now, just think about like, why could it be failing and what could possibly be done to remedy this? But until then, let's go brag about it some more because it's the first time we got time steps in neural networks. Let's enjoy ourselves. So what I talked about before was French to English or English to French, vice versa. And RNNs are the first model that can actually go about letting us do this with a neural network. Each language has a different structure, order varies, single word can mean many different things. So for example, this word might even map to multiple words in the second sentence, or a word might have to be included. In the English to French representation, the le is only in the sentence below, not included in the sentence above. You can even argue there's differences in the translators. Maybe translators don't output the same representation every time because languages are just imperfect. You can't always cast one language to another language with ease. And so sometimes there might even be order differences in sentences. Things that arrive in one temporal order are totally flipped in the second one. And the recurrent neural network lets us actually take advantage of that. And the great statement here is what I said before. Dictionaries don't get us where we want. You cannot always monotonically translate one word in the same order and output it in the same order and assume you solved your problem at hand. So seek-to-seek models, or generically what we're proposing here with an English to French translation, is taking in one sequence and outputting another sequence. This is the big seek-to-seek word, the fun thing that gets talked around. And this is actually a powerful model. This way of thinking hasn't gone away. The only thing that has changed is the models. Sequence to sequence is always going to be here as long as we need to translate things, or as long as we need to take in questions and output answers. I mean, that's still what everyone cared about in ChatGPT. We're still doing sequence to sequence, but it just looks like a lot of different things. So don't disparage sequence to sequence, but maybe disparage the way we're modeling it. Maybe disparage the way we're doing math and the way we're trying to optimize over variables, because you can critique that forever. But at least right now, we've given our first crack at solving sequence to sequence, taking in one sequence, outputting another sequence, and it's nothing to scoff at. This should be taken and enjoyed. So again, let's say we're using RNNs for our example here. We can represent this by taking a singular recurrent neural network, translating il, and top. Not going to pretend I know French. Pass that through. The hidden state communicates forward in time. And this was the great advent. This is the great thing that we've been bragging about for the past, 30 minutes or so, is that we can pass it forward in time. But now the innovation, or the thing that we have been able to do something totally new, is that we can pass it forward again and actually start passing in English sentences and start seeing if we can predict what would come next if this was an English sequence of text. So here, what we actually do is kind of decompose the two. One might say that English and French are two quite different languages. So maybe we should actually have representations that encode the two differently. And so what they said is that if we're starting with French, we should actually maybe just start with a model that encodes French and then train a separate model that can decode English. And that's what they do. They pass in French to one recurrent neural network. It passes the hidden step forward in time. Then it gets passed into a decoding neural network that's in English. It takes in an English sentence and tries to output the next word in said English sentence. And there's fun sampling things you can do and talk about all the 70 and 126 methodologies to actually go and derive these tokens. So it's not as simple as you might imagine. So this is, or the first model you get passed into is what I called the encoder. It encodes the information in one modality. And then the second one is a decoder because it decodes the information from the other modality. You can think of any encoding model as encoding some sort of vector representation, then any decoder model as actually taking a vector representation and outputting some sequence of interest. In this case, it's outputting our English text of interest. And the way that we let these two actually interplay with each other is this big arrow to the right in the middle of the model. If there's anything from the lecture you take away, it's just look at the arrows in the middle of the model. That was the big thing that we did. And so the big thing in sequence modeling is that we take the last representation from the French sentence, and we take the hidden state and we pass it forward to the beginning of the English decoder model. And this is what lets us go from sequence to sequence, from English to French, or French to English in this case, and actually kind of keep that modeling representation. Because thanks to AutoGrad and thanks to all these like fun, lovely inventions that we have, we can actually go about keeping in mind some of these variables within time and calculating gradients with respect to them, but letting the two models communicate.
I have a question.
Yeah.
If we're going from like French to English and English to French, do we need 2 models or 4 models? Like, does English to French require 2 separate models and French to English 2 other models?
This is a perfect question. So you could go either ways. Maybe there's a paper that says one is better than the other, but you can actually do it quite either way. Oftentimes people find that these encoder models work just as good as decoders, but these decoder models also work great as encoders too. So you could have exactly what you're saying, one just universal English model that serves as encoder and decoder, or you could also have 4 different models where you have one encoder English model, one decoder English model, then one encoder French, one decoder French. And this is the exact paradigm that you should kind of be keeping in mind. Is sounds a little cumbersome. Sounds a little challenging to have to like keep all this at once. Then there's an even more reductionist point of view that you could have where you're like, you know what, language is language. What if we just have like one big model? Kind of where things head today, where you're like, you know what, the training many small models is challenging and expensive and makes us pay our engineers more. So we could skip that step and just kind of smack it all into one model. And that's kind of what people are thinking right now. There's a model called Bloom that was trained by Hugging Face last year, 2 years ago, something like that. Open source large language model. And they're just like, we can train a single model on every single language, kind of call it a day there. And it works pretty well. It's not competitive with other models, but like it works well. Solid answer.
Yeah.
Awesome. Of course. And again, just rehashing out, when decoding, all that the decoder is actually doing is taking a singular token and trying to predict what should come next. Just taking everything preceding it, the hidden state and the current word, and trying to predict the output. So what's the intuition behind this? It's simply just that the previously outputted words should probably be the context for what you're trying to say next. You can argue semantically that like humans probably don't speak this way, maybe like propose a sentence, then iteratively refine it over time instead of just being like a bot that goes from word to word to word in a really monotonic fashion. But you know what? It's gotten us this far and works really, really well today. The paradigm that you can go from one word and just predicting the next works better than we'd like to believe. Doesn't feel scientific, but it's quite empirical that framing a problem this way works really well and is really tractable to solve computationally. So that's food for thought. Like, this is a stupid idea that you can predict everything intelligently going from one word and only thinking about the next. Shouldn't there be some sort of like more challenging representation in the middle? Shouldn't we be thinking about ways that we can maybe think more challenging about these contexts? Researchers have kind of proposed methods that like overcome what I'm talking about right now, where you're only taking one word, predicting the next by giving models like a backspace token or letting them write things down on a notepad so they're not just like belligerently speaking in between like coherent thoughts. But these are all things to keep in mind. Why does sequence to sequence work? What are the flaws of the ways we're even thinking about sequence to sequence right now? And in particularly, what could potentially be wrong with like using our current neural network? What are we throwing away when we're taking in this modeling paradigm? So now we get to my favorite part, which is tearing down all the literature. Why does this suck? How can we make it better? And maybe what are ways that we've made this better and spoiling some of the future lectures ahead? So that fixed length vector I've been talking about and kind of elucidating it before, 512 dimensions is not nearly enough to get through the kind of information you want. Let's say we're actually reading a whole book. Let's say we're reading War and Peace, and by the first token, you know, first 2 sentences, maybe we can keep all that in mind, who the characters were, what we're actually talking about. When you're on the last page of the book, do you think in a 512 dimensional space alone, you're actually going to be able to remember every single piece of information and content within that book? Maybe if you had some perfect mathematical space, but I'm doubtful that you'll be able to do it with finite computation and discretized arithmetic representations. It's just not happening. So how can we go about improving that? And what are ways that we can think about maybe giving ourselves more than just a singular vector to communicate all of time and all of history to our model in the future? And this kind of encoder-decoder paradigm, the way we have to get them to perfectly match up and quantize, hasn't really been solved, but maybe one of you will actually go about doing the foundational research that does solve this. Is there a better way than just drawing the arrow or quite literally doing addition to make these models communicate with one another? We have methods that we'll talk about in transformers with cross attention, maybe being able to look at these components a little bit differently, but there's not been a great method or a great novel revelation that we've had in how you can overcome this. And how can we even go about recovering lost information? You can't. As soon as you've overwritten some sort of history in your vector and you overwrite that history, that information's gone. You can't recover it. You'd be breaking information theory if you can somehow recover lost information from a sequence with no ability to look back at the sequence and query something you wanted. Future models that we'll talk about, in particular the transformer, kind of overcomes this, but it still has its own limitations. So be skeptical. Think about everything and think about why it probably sucks. That's how research and great research is done. Think every word that I'm telling you is complete garbage and try to make your own interpretation of it. So again, what time is it? We go from step to step to step, and we'll have this ever-evolving hidden vector. How do we fix this? Like I've been elucidating at, there's something called attention. Attention is this, actually not even derived by Google, but Google made a better paper that uses attention. It's basically the fact that you only care about a few things at once. And what if we only have to compute with respect to the few things we care about at once, instead of like staring at every single word, swishing it through like a singular vector and trying to get that to communicate? We can propose a network that they call the transformer. And it's essentially like ResNet with an asterisk is the greatest way I describe it. It solves one thing that ResNet solved, which is like getting good gradients. Gradients are hard, gradients are challenging, everyone uses AutoGrad. And how do you actually get like 100-layer neural network to converge? The secret is use addition. That's at least what I think the great takeaway from ResNet is the field rediscovered that addition is really good, because the derivative with respect to addition is just whatever your input sequence was, or whatever your input token was times 1. And the way that comes into transformers is we use that same idea to stack more and more and more layers. But the way that we actually get this transformer to do something more than just be a glorified ResNet is we propose attention, which lets you selectively look at elements of the sentence and do computation based on those elements alone without having to care about some 512-dimensional vector that you're probably like losing half your sentence in. And the other great thing that attention does is it unpacks one of the key things that we've kind of subsumed in this RNN model, which is an underlying for loop. If you learned anything in computer science, it's that everything is its big O computational complexity. And if you have a for loop, automatically have O of n. So anytime we're trying to predict the next token in a sequence, or at least do our pre-training task, we need to generate the hidden step at every single time. That's a for loop. That's immediately O of n. And we're wasting flops. We have expensive computers. You have computers with thousands and thousands of GPUs that you're letting sit idle because you're waiting to get the next time step. That's just not going to cut it. And that's not what let us get the breakthrough that we have today. And so I believe in Wednesday, and then next week when we talk about vision transformers, and I sound like less of a kook and tell you that there's a way that words actually map back to images. You'll see why attention, and in particular transformers, go and solve some of these fundamental problems that I posed to you today. So now we're going to return to the beginning. I've built up recurrent neural networks, and I've built up most of the math that allows them to succeed, and then proceeded to tear it down and tell you that just wait 2 days from now to learn about this newfangled model by Ashish Vaswani, and it'll be great. Life will be great. We solved all of machine intelligence, at least that's what some people think, on Wednesday. So what are we talking about now with embeddings? At the beginning, I subsumed the fact that we can turn every word vector, or every word, into a one-hot vector, which is just a bunch of zeros and a singular one. And then we're going to go do some fun linear algebra next. That's all that deep learning is. How do we go about using these one-hot representations in a much stronger way than just ones and zeros in a matrix? That is where we come to with embeddings. So oftentimes data is high dimensional. Our tokenizer representation is high dimensional, as is maybe we have a vocabulary of like 60,000 words, and we're taking up most of the vector with just zeros. That's a very expensive waste. Your boss will probably have questions about why you're using up so much memory to compute nothing. And how can we start getting something a little bit more compact? We could try using binary, maybe that'll get us somewhere. Or we can kind of stick with this one-hot paradigm, but think about smarter ways that we can do it. Maybe we could do something with orthogonality. Maybe each word is a little bit orthogonal. There's some small components you can add up. So you've at least got independence. You've at least not wasted all this compute memory that you have, but still not getting there, still not great. Now, the answer that I've been withholding is the great answer in all of deep learning is if you have a problem, just learn it. Don't think too hard. Make the computer think for you. And all we really do is we still keep those one-hot vectors, but you essentially construct a matrix multiplication, or the way this is kind of implemented under the hood is a dictionary lookup, where you have this big matrix of all your one-hot encodings and an exact vector that it should represent to. And this is differentiable because matrix multiplication is differentiable, or what we're actually doing is matrix lookups, which is also differentiable. And now we've constructed smaller representations, like maybe we have our 50,000 words, and we're squashing those 50,000 words in a one-hot vector down to maybe a more manageable, 2048 dimensional space, where it's continuous and it's not filled with zeros, and we're not wasting up computer memory. And there's many ways that we can go about doing this. The way modern things work is you literally just stick this weight matrix in and you learn it through backprop, your normal autograd. And we can also even choose those and learn them in smart ways. NLP, before deep learning was real cool, or even while deep learning was cool, thought that there are some fun ways that you can kind of derive vector representations, and they call that word to vec. Some cool reading there, and there's some cool linear algebra you can do, where you actually operate. One example is king minus man plus woman, and you look for the nearest vector in latent space, which actually output something like queen. And so you can get some of these fun little semantic plays going on if you have these meaningful representations of your tokenized words. And this gives us more control now over our compression, since we've no longer wasted so much memory with zeros and ones. So core idea, reducing dimensionality. Take a big, useless, very, very large vector. Now we're actually just operating on integers and then taking those integers into a vector representation and saving a lot of time and saving a lot of memory. And this will also be more intelligent because we're optimizing what vectors it maps to. And if there's literally any lesson in all of deep learning, if you have something that you want to try to model, is there a way that you can parameterize it and make it so you're not hand encoding it, but instead letting the computer optimize it for you? That's exactly what we do. That's the exact success of embeddings. Now there's one more weird and finicky one, which is positional encodings. It's not going to be immediately clear why positional encodings matter in this lecture, but if you can hold out for the lecture that happens on Wednesday, you'll get to why it does matter. So stick with me. Believe me, I'm about to tell you a bunch of stuff that sounds like BS. It actually sounds really stupid. When I first read this in the paper, I was like, that's maybe one of the dumbest ideas I've ever read. I don't know why you guys are hired. What lets you keep the lights on at home? A lot of demeaning things you can say about positional encodings, but they work and they'll inspire one very important thing. So let me tell you a stupid trick that works very well, and then I'll tell you exactly what that enables. And on the lecture on Wednesday, you get up to my beloved transformer, which is what's let most of modern deep learning actually succeed. And in particular, modern computer vision take one final large leap forward. So one way that we've been representing time is the recurrent neural network. We have this weird hidden state that goes forward. I'm going to make an argument that we don't need a hidden state that goes forward in time. We can instead transform every single token, every single word all at once instead of our super for loop. So we're going to get rid of the for loop. But if we're going to use the same sort of operations to parse through everything in a sentence, how on earth do you encode time into that? How do you encode that you're actually somewhat different than that? Because if we take our normal R paradigm, get rid of our hidden state because we don't want the for loop, how can we introduce some sort of temporal notion into our model? And my answer is, without this weird finicky trick we're going to learn, you really can't. There is no way that you can induce time into your data just on having some sort of weird weights alone. You need some other way that you can give your model a notion of what goes where. What word goes where in a sentence, and where are you attending to, and where are you operating on at a single point in time? So we want a few major goals. We want to output a unique encoding for each time step. Like time step 1 should be different than time step 2. Fairly easy. Next thing, we want the distance between two time steps to be consistent across different lengths. So let's say the first and third character should have an equal notion of distance to the third and fifth character. That kind of uniform representation should withhold. And now the more challenging parts are that we want it to generalize to longer sentences without any effort. So 4 words in a sentence kind of sucks. How can we get to like 1,000 or 1,000,000? Peter Beal's lab just had a great paper that showed that a few algorithmic modifications to this transformer algorithm can actually lead you up to 10 million samples. How do you go about creating a vector representation that withholds up to 10 million samples? And then lastly, it needs to be deterministic. Randomness sucks, no randomness. Let's go figure out something deterministic. So one initial way you might be thinking about this is binary encodings. Binary encodings have some nice properties. They change at every time step. It's nice. There's different parts of it that change at every time step. So that means you have like many different bits of information that you're conveying from time to time. And there's also a nice property that kind of alternates back and forth to those higher bits. So there's some sort of long and short-term temporal dependency that you can build up among bits. But the issue is that we're discrete. And discrete things are hard to optimize over. Go for it.
Is the lecture QR code?
Very end. Am I over time? Yeah. Let me skip to that and then I'll basically jump to all this.
You can place the QR code and the QR code is given this issue master. So
and while everyone's filling out attendance, I'll jump to the end of the story. There's one simple thing that you can do, and that is addition. You can just add some function to every single time step in order to generate your positional encoding. What you can actually do is use sinusoidal functions and cosine functions with differing temporal frequencies and just add them to your vector representations at each time step. And that'll give you a notion of different time steps within your sequence. And that'll enable the big breakthrough that we'll talk about on Wednesday.
Yeah, I think it doesn't.
can you?
Refresh.
Yeah. I did a big.
Yes. Yeah.
While everyone's filling out the attendance form, do you have questions? I talked at you about an idea that we built up, then proceeded to tear down over the course of the lecture. Not at all about computer vision. Are there any things I can help elucidate or talk more about? Life questions, transformer questions, read a paper you like, read a paper you hate. Happy to talk about papers. It's 8 o'clock, so you guys are all free to leave or happy to stay and chat if you have questions. Anyone's interested in machine learning and its intersections with biology, more than happy to chat.
I actually have a more about my interest question. So I'm very interested in what you just talked about, the different modeling. But I think I'm not fully understand about the mathematical or the very theoretical mechanism behind all those models. Is there any recommendations of papers or reading this?
That build up the theory work behind it.
Yeah.
What does theory mean